In this problem, we are going to learn how to draw phasors for a particular circuit. The circuit we are given has an AC generator operating at 60 Hz and producing an RMS voltage of 120 volts. It drives an RLC combination in series with the value of the resistance R equal to 175 ohms, the inductor 90 millihenry, and a 15 microfarad capacitor. Here is the circuit diagram. So the generator drives an R, L, and C combination in series. Before we draw the phasor diagram, let's go ahead and compute the values for the inductor and the capacitive reactances. So the numerical values turn out to be the following. The reactance from the inductor is 2 pi times 60, that is the frequency, 2 pi f, that gives us omega, times L, which is 90 millihenries, written as 0.09 ohms, and the total product turns out to be 33.5 ohms. In a similar manner, the capacitive reactance is 1 over omega C, and the value of C is 15 microfarads. I've written the microfarads in a slightly different way, so we keep the 10 to the minus 3 part of the 10 to the minus 6 at the bottom, and we put the other 10 to the 3 on top. This is just for ease of computing and checking, and it turns out that the final value of the capacitive reactance is 175 ohms. Now this value turns out to be a little bit bigger than the value given for the resistance of the resistor, 175 ohms. So now let's go ahead and draw the phasors. We start by establishing a coordinate system. That's the x-axis, and by convention all real-time voltages are expressed as the projection of the phasors on the x-axis, and we establish the y-axis, of course, and the convention is that at some time t equal to 0, the chosen time t equal to 0, we start out with the current pointing along the x-axis, and at some other time t it would have rotated at the rate omega to some other angle. So let that angle be as shown here. So that's the maximum current in the circuit, or the current in the circuit, and the actual value of the magnitude of the current in the circuit is given by the projection of this vector along the x-axis. And this current, of course, is the same in all three components, R, L, and C. Once we know the current in the resistor R, we can calculate the voltage across the resistor, and those two quantities, the current and the voltage in the resistor, are in phase, and therefore the direction of the voltage across the resistor has to be the same as the current. So that's shown here. The magnitude of this vector is different. It's typical to show that since we are multiplying this I'm current by some quantity r, which is greater than 1, I've just shown this vector to be longer than the given vector. Now the current, of course, through the inductor and the capacitor is the same, but we know that the voltage across the inductor leads the current. So therefore the voltage across the inductor has to point in this direction, and the magnitude of the voltage across the inductor, the instantaneous value, of course, is given by the projection along the x-axis, which turns out to be negative in this case, but the magnitude of the maximum value of the voltage across the inductor is just the maximum value of the current in the circuit times the reactance XL. Similarly, for the capacitor, we know that the current leads the capacitor, therefore the voltage lags it by 90 degrees, and it has to be in this direction. And furthermore, it's exactly opposite to that of the inductive voltage. The value of the arrow here, the magnitude of the vector here, is slightly larger than the magnitude of the vector along the voltage along the resistor, because of the slightly larger value of the reactance on the capacitor. So now the total reactive part of the voltage would of course be given by the difference between the inductive and the capacitive parts, and that's shown here by the bluish arrow. And given the total reactive value of the voltage, we add that vectorially to the resistive component of the voltage. Let's go ahead and do that. And the vector addition of these two voltage values, I max R plus I max times XL minus XC, turns out to be in that direction. So this is the maximum value of the voltage. It has a relationship with the current in the following way. So that's the angle between the voltage and the current in the circuit at all times. So this entire arrangement rotates at the angle omega. The instantaneous value of the voltage uh, by the projection of this arrow along the x-axis, and that's the instantaneous value that the generator is producing, because that is the total voltage.